Our first plenary speaker today is Britt Lundgren from the University of North Carolina at Asheville, who I overlapped with for a while at NSF. Britt did her undergrad work at the University of Chicago and her PhD work at Illinois. So we have an all Illinois alumnus set of plenaries today. Her research focuses upon stellar populations and star formation histories of distant galaxies and the evolution of their gas and dust content. Britt is currently serving as the co-chair for education and public outreach for the 4th generation of the Sloan Digital Sky Survey. And she's going to talk to us this morning on incorporating Sloan data into astronomy education at the high school and college level. Please send a warm telepathic welcome to Britt Lundgren.
Hi, thank you, Kevin, for that great introduction. Thank you, Stephanie, for all your help organizing. I'm really pleased to be here. For my entire teaching career, been using UNL's interactive astronomy simulations. So I feel really honored to be included in this group of really, truly innovative educators in astronomy. So thank you for the invitation. I'm going to quickly see, share my screen. Right. Okay, so if at any point my video or sound drops out, just please let me know. But I'll go ahead and get started. So as Kevin said, I'm going to be talking today about some work that I've done with a large team of collaborators in the Sloan Digital Sky Survey's 4th generation. We have a kind of working group, a core team of people who specialize in helping bring the data from this very large project to the public and to educators and students. And I'm really excited to be sharing with you some of our resources today. So there are a few major points that I want to cover in my talk this morning. The first is to kind of motivate why I am such a firm advocate and evangelist for using real data in astronomy education. And in fact, if you're using real data, why not use big data? So I'm going to motivate that to begin with, then tell you a little bit about the different kinds of data that the SDSS has made publicly available in a very large database. And then I will show you some resources and demo a couple of things that students have done in classes that I've taught here at UNC Asheville, and some work that's been done by my colleague Rita Tugero, who co-chairs the education and public outreach team with me. And she's located in Scotland at St. Andrews University. So I'm going to be providing a link to all of these materials that I'll kind of be showcasing today. I think Stephanie's already provided that in the chat window, but I'll also throw it up on a slide in a little bit so that you know where to find all of the things that I'll be sharing. So to start off with, why do I think it's important to use real and big data in your astronomy classroom? First and foremost, I think there's a growing amount of evidence that student engagement with real science data has a positive impact on their persistence and interest in STEM careers. This is just one figure from one paper in 2007 that shows the impact of research opportunities that undergraduates were engaged with, and the impact that those experiences had on their perceptions and interest in STEM. So what you can see here from this lovely pie chart is that it's overwhelmingly positive. Only fewer than 10% reported that such an experience had actually had a negative impact on their interest in science. So we know that engaging with real data has positive effects. And in fact, the sooner we can provide those kinds of opportunities for the public and for students, the better, because there's also a long list of evidence showing that students are making up their mind about science and their feelings toward it and their likelihood of pursuing science careers around middle school. 8th grade seems to be a really important turning point for students in terms of their future direction in science. This is just one figure from one paper of many that have shown evidence that this is the case. But what's shown here are the fraction of students that are achieving bachelor's in STEM fields, split left and right by students who in 8th grade suggested that, that they could foresee that for themselves in the future. So students who thought that they might become scientists as early as 8th grade were twice as likely to actually complete a science degree in college. And so the earlier that we can get students interested, the better. And we know that real engagement with science and data and scientists can provide that kind of interest. So, so of course, you know, I'm preaching to the choir. You're all science educators, so so you probably already know everything that I've just said. But this has been not just a priority of educators over recent years. This has been a long-standing priority of the federal government for decades, right? And every few years, the National Science and Technology Council produces a really large document outlining the current status of STEM education and the STEM workforce, and a path forward to maybe improving our position. So every administration produces these reports. I'm just highlighting one from the Obama administration in 2013, which really stressed increasing engagement as well and set real goals for what that would look like to produce more STEM graduates and have a stronger STEM workforce, which of course we all recognize as a way of growing the economy and also growing individual individual family earnings even. So this is a good federal goal to have, and it's shared across administrations, across politics. Everyone likes this idea of building a STEM workforce. I'm including here just a quote from the Trump administration's recent report in 2018, again from the National Science and Technology Council, which stressed convergence of disciplines as a way of encouraging interest in science and looking for interdisciplinary experiences as a way of stimulating interest in STEM. And I want to just kind of take off on that point and say that I think astronomy is one of these disciplines that really does cross over into all of the STEM fields. Historically, astronomy has really strong ties with physics. You know, there are major laws of physics and you know, fundamental components of the universe that were discovered by astronomers and are now, you know, part of our canonical understanding of physics. But of course, you know, as the technology expands in astronomy, as we move into this new and growing field of exoplanets, for instance, we have increasing crossover with chemistry and biology. There's a lot of work done in astrobiology now, which will certainly only increase as we start modeling exoplanet atmospheres and thinking about conditions for life on all of these, these growing numbers of Earth-like planets that we're increasingly detecting. But of course, as the computing and you know, engineering advances of astronomy have increased, so has the crossover between those fields of computing, engineering, and math as well. And so astronomy really is kind of a place where all of the STEM disciplines can kind of converge, and you can find a lot of interdisciplinary crossover. It also makes it a really great gateway for getting students into any discipline in STEM. So I may be biased because astronomy is my field, but I've seen this to be true with students that I've worked with. So why big data, right? Why should we be not only excited that we're teaching our students astronomy, but why should we be encouraged to to expose them to big data in our astronomy classes? The number one reason that I would say is that astronomy is increasingly reliant as a profession on big data. As the technology has increased in recent years, we've moved from maybe 20 years ago being in a regime where data was on the order of gigabytes to 10 years ago, where astronomical data that you're wrangling as an astronomer is moving into the regime of terabytes. And now, you know, just in the past 5 or 10 years, we've moved into this era of petabytes. There's a huge amount of data being taken and stored, and analyzing it has really unique challenges that are relatively new, even if you consider that that astronomy has historically been kind of one of the bigger data sciences. What I'm showing here is a plot of the growth of the amount of data being stored by the Space Telescope Science Institute, which manages mostly space telescopes, as the name would suggest. And you can see how the amount of data that they've been storing over the past 10 or 20 years has been increasing, and is planning to increase even more dramatically in the future. And the Y scale here is terabytes, right? And it's in thousands of terabytes, which puts you into that petabyte regime, which most people probably don't even have in their kind of lexicon of storage. But that was only space telescopes. So we are on the horizon of the start of a new, really large data survey, the LSST survey, which has recently had its telescope renamed to the Vera Rubin Observatory. This is a big US astronomy project that's being built, is almost completed now in Chile. And the goal of this project is to repeatedly scan the night sky for the first time, really statistically looking for how things change in brightness and position on the sky, not just taking still images maybe once every 10 years, going back to it and seeing if anything changes, but doing this repeatedly on a really short cadence. So this will open up a whole new window of time variation in astronomy that really hasn't been accessible before. But of course, as you might expect, repeatedly imaging the night sky every few nights is going to build up a lot of data very fast. In fact, they're expecting about 20 terabytes of data to be newly produced every night at this telescope. Even getting that data from Chile to the US is complicated. It involves a lot of infrastructure for high-speed internet cables that are laid through the ocean. It's a really complex logistical problem. And then you get to the problem of actually analyzing that data, trying to find interesting signals in this ocean of information. And so this is something that students of astronomy and professional astronomers will be doing as part of their daily work very soon. So of course, the Slant Digital Sky Survey, which I'm proud to be a part of, was an early kind of explorer in this era of big data astronomy. The goal of this survey, which had first light in 1999, so about 20 years ago, was to produce the first large digital map of the sky. So mapping the night sky, about 30% of it in color, and then also in 3D using spectroscopic observations to measure redshift and actually get a third dimension of information on this map. So this was really producing the first truly large data set in astronomy, and it required a lot of work to produce the infrastructure to store that information and make it accessible to scientists and the public. And so this effort, which Gail did a really great job of introducing during her talk last night, if you were there, was a productive collaboration between academic astronomers and computer scientists at Microsoft, and they were arguably very successful in making a functioning database that has opened up this very large data set, not only to the astronomers who are using it to uncover new patterns in the universe, but also to make it accessible to anyone else in the world who's interested, right? And this has made it a really rich space for explorations in the educational realm. So building curriculum around this data set has been something that has only been possible because of these clever online searchable databases. And I just wanted to highlight one line from this paper that described what would become the Sky Server, is shown here, predicting that astronomers would in the future need to be equally good at mining data as they are at using telescopes. And I can certainly attest that this is definitely the case. In fact, I have to admit, I think I'm much better at data mining than I am at using a telescope. Sometimes that flusters me a little bit, whereas I've grown up in the Sloan and spent my whole career working with these great databases at my fingertips. So there really has been kind of a sea change for many astronomers in the field that began with the Sloan Digital Sky Survey. Okay, so of course, most of your students are not going to become astronomers. Most of them probably aren't interested in becoming astronomers, right? But many of them may be interested in going into STEM careers. They're exciting jobs, they're well paid. And so I think, you know, all of us are in the business of making that possible for students who are interested. And so I would argue that including big data in your astronomy and physics classes is worthwhile for those students as well, if only for the reason that most STEM jobs in the current US economy are in fields of computing and data science, right? Maybe you can't read this bar chart, I'm not sure, but the biggest contributor to different types of STEM fields in the US economy as of 2015, as compiled by the Bureau of Labor Statistics, are in computer-related fields. The light blue here is engineering, and physical sciences, which, you know, most of us are teaching, is this little orange bar at the top. Okay, and so it's not only that computer science and data science fields are a majority of the existing STEM jobs, but they're also the fields within STEM that are most rapidly growing. So computing related applications occupations are where over the past 10 years, we've seen the most growth. That of course may not always continue to be the case, but in recent years, it certainly has been by a long shot. And so it's worth preparing students, or at least giving them an introduction to computing and data, because that's where a lot of the jobs are. But of course, many of the students that we teach aren't even interested in STEM jobs at all, right? And I would say it's still worthwhile to introduce them to the concepts of big data, analysis, visualization, wrangling of data sets, et cetera, if only for the reason that they're growing up in an information age. And unfortunately, increasingly, we're not only just being exposed to information and data in our daily lives, but increasingly also misinformation and disinformation. So I feel like it's part of our duty to help students have the kind of basic data literacy skills that can allow them to be better consumers of the information that they are exposed to. Just as one example, I'm just showing a snippet from a paper from 2016 that investigated how misinformation spreads on the internet. What you're seeing here is a curve of the distribution of lifetimes of stories that have propagated on the internet. The orange here are legitimate science stories and how long they spend in circulation on average, right? Most peak around a few hours, but some live for a few days. Interesting enough, the conspiracy stories that propagate on the internet have a similar distribution. So they're spreading in a similar way as legitimate science stories do. So that's not great in terms of if you wanted to measure the average person's ability to differentiate between real science and conspiracy, for instance. Unfortunately, even though they have similar distributions in their average lifetimes, the amount of people who receive the story in that same amount of time is not the same. So conspiracy stories or fake news, right, is shown on the left here. And those that live for hundreds of hours on the internet reach many, many more people than stories of legitimate science, which spend the same amount of time circulating online. So we do see that misinformation propagates readily on the internet. And I'm sure if any of you have been on Facebook in your life, you're aware of this. But this is something that we should be working on, making sure our students can recognize as they go out into the world. And of course, especially now during the pandemic, in the time of COVID, it's even easier than ever to see misinformation or the sharing of data misrepresenting the reality of a situation, unfortunately. And so one good example of this, one classic example from a few months ago, is this image of COVID rates in 5 counties in Georgia that was published by the Georgia Department of Public Health. So of course you have case rates on the y-axis and time on the x-axis. But if you were to zoom in, you would see that the order in which these case rates have been presented has been completely jumbled up, which would lead someone who's just glancing at the figure to have the wrong takeaway from this plot. So increasingly, people are working on educating students to be better consumers and more skeptical of the way data is presented to them in their daily lives. There's a brand new book out by a couple of faculty members at the University of Washington in Seattle who have produced an enormously popular course that teaches all about data literacy and shows lots of examples about how information can be misrepresented. And so anyway, so I think this is a really important topic right now, especially in education. And as scientists, we have the ability to make our students aware of how data is represented and to be skeptical of what they see. Okay, so generally, just to put this all in a nutshell, to motivate, I think it's important that our students become capable of analyzing data themselves, and any kind of hands-on data intensive classroom activity can help promote better data literacy, better computational literacy, analytical thinking. And of course, this is something that I have seen to really be the case in my classrooms. It's also a way of preparing students for higher level research opportunities, right? If they feel like they have some data competency, if they maybe have a little bit of programming on top of it, they're going to be really competitive for RU opportunities, for internships, and that can really set them on a path to an exciting career. Okay, so I'm going to just step away from that basic motivation. I'm sure I'm preaching to the choir. And now I just want to show you some of the different kinds of data that we in the Sloan Digital Sky Survey have made available to the public over the past 20 years of survey operations. So let me just back up in case any of you weren't able to attend Gail's talk last night and just briefly introduce what the Sloan Digital Sky Survey is. So this is an international collaboration of hundreds of scientists across dozens of institutions around the world. And the goal of this survey in the most general terms is to map the sky in both 2 dimensions as images and in 3 dimensions using spectra. And the scientific goals of making these maps are threefold: to study the composition of the Milky Way, to also study the compositions and kinematics and locations of nearby galaxies, and then the large scale structure of the cosmic web. And by studying how that changes at different redshifts or different look back times in cosmic history, we can start to understand more about the expansion history of the universe over billions of years. So these are the main science goals. The education and public outreach team, which we refer to as the EPO working group, has the goal of making the engineering science results and data from the SDSS accessible to the public and to students and educators internationally, and through a few primary mechanisms, through formal and informal education resources, through citizen science, most notably like the Galaxy Zoo project, which you've probably heard of before, and then also through blogs and social media. So you may be already following us on either Facebook or Twitter. And if not, look us up. So we have a really large team. Gail is the new spokesperson of the survey. We're currently making the transition just right now from the 4th generation of the Sloan survey into the 5th generation, or Sloan 5. But our current education and public outreach team is really shown here as the core group from the 4th generation. Some of us are going to be kind of exiting and handing off the baton soon to the new team. But I'm just showing you here this slide of all these people to make the point that we really are international. It's a great working group. We meet a few times a month, and produce bilingual materials and run workshops around the world. And it's a really great group of people. So what is the Sloan Digital Sky Survey doing, right? So I said that we're making maps. And in the first decade of the survey, the goal was to make one really great big color image of the night sky using what at the time was the largest digital camera in the world. And then in addition to the imaging, our multi-object spectrograph, which could take 640 spectra simultaneously, was building up a three-dimensional catalog of the positions of all of the stars, galaxies, and quasars that we targeted, and building up what would be over 1 million spectra in the final sample of that legacy portion of the survey. In addition to the big map, right, there were also a couple of science goals in that first 10-year period of the survey. One was to repeatedly re-image a part of the equatorial sky to look for things that were transients. And the goal of this was to look for new, new supernova. And that was kind of a rare kind of part of the survey that was doing repeated imaging. Most of the survey operations were just getting enough information to cover the sky once and moving on so that you could slowly build up this really large map. Another specific science goal of the early survey was to measure the stellar populations of stars that were in the halo of the Milky Way galaxy and also in the thick disk. So a little bit of study of our own Milky Way galaxy, in addition to mapping out the large scale structure. Excuse me. So at the end of that first 10 years of the survey, we were left with a large map. This is known as the orange spider diagram. And what you're seeing here, if you can make out the kind of clumpiness of this diagram, is the positions of galaxies in the night sky. And this is the big part of the night sky that you can see from the northern hemisphere, and then a little bit of coverage that we also get in the south. In total, we have more than 30% of the night sky as visible from Earth covered in this imaging. And because this was such a major achievement, the camera that was used to make this image now has a place in the Smithsonian. Unfortunately, not on the main floor. It's down in the archives, waiting for a good time and place to be displayed. I think it's down there with the Ark of the Covenant. But here's an image of it before it was kind of packed away and stored. So like I said, all of this data is available, and you can explore the entire imaging footprint of the Sloan using the Sky Server, which was, again, built through collaborations with industry computer scientists and astronomers in the Sloan. And this is just an invaluable tool. It's great for students and the public, and it's equally useful for professional astronomers. I'm not going to show you how it works just now. Some of you have probably seen it before, but we will be covering this in our workshop this afternoon. So if you're able to come today at 2:30, we will walk you through it and show you some fun scavenger hunt activities to do with students of all ages. Everyone loves the scavenger hunt. So in addition to all that imaging, we also have, millions of spectra that are available, which have been taken with these iconic aluminum plates that are drilled to match a small portion of the sky. So each plate is unique, and each plate is used, well, most plates are used once or twice before they're retired. And the kind of, great engineering advance of these plates was that you could take so many spectra all at once. So you have a unique fiber optic cable that plugs into each one of those 640 holes. And when you plug the whole thing into the focal plane of the telescope, you can collect spectra for 640 objects simultaneously. And so this was the way that we were able to make the maps three-dimensional. By getting their spectra, you get a redshift. You can see how much the light has shifted into the red, and that gives us a good measurement of where that galaxy or quasar is located in terms of its distance from us. So each of these iconic plates is hand plugged by a dedicated team of observers that work at Apache Point Observatory in New Mexico. We also have plates that are plugged and being used in the southern sky in the current version of the Sloan survey. So we also have people doing this in the south, but it's an enormous amount of work. And in times of the survey where we have really great weather, we really put those observers to work. So here you can see they're all bemoaning that their fingertips are rubbed raw from plugging all of those plates. But we truly couldn't do the work of the survey without all of these great efforts. So what I'm going to show you now is all of these. Here is one of our dedicated observers swapping out some of those plastic plates and where the dome of our telescope actually rolls off. And the telescope itself is on this perch overlooking the valley below, because the air currents are particularly good in that region for getting good seeing of the night sky. But if you look far enough away, you could see white sands in the distance, kind of giving you some idea of where this is located in New Mexico. So as a result of producing these large three-dimensional maps, we have produced iconic images of the large-scale structure surrounding our local position in the universe. This is where we're looking. You look out and make maps in 3D, you can actually see these kinds of wedges of structure with clusters of galaxies and voids in places where they're underdense. And this is really showing us kind of the sponginess of the large-scale structure in the modern universe. And the, while maps like this had been made before, Sloan did it at a kind of different scale. And we now have these beautiful abilities to kind of fly through those three-dimensional maps. And oftentimes, if you go to a planetarium, you might see something like this using real Sloan Digital Sky Survey data. There are versions of this fly through that you can experience with 3D goggles, which are really crowd pleasers also. But this is all a visualization of real positions of real galaxies in our local universe, which were made possible through these observations in the Sloan. And this visualization was put together by Mark Subarow and collaborators at the Adler Planetarium, and it's a definite crowd pleaser in every class that I ever teach. Okay, so all of those spectra are also available. It's a little higher order activity to introduce spectra to your students, but if you want to, through that same Sky server, you can access the Science Archive server. through some simple navigation, and this will allow you to find interactive spectra for all of the millions of objects that we have collected. You can zoom in, you can mark emission lines, which tell you about the composition of each of these stars and galaxies that we've recorded. And so these are really great interactive tools for further investigations. So the more recent versions of the Sloan survey have had more specific science goals as part of this overall mapping strategy. The Apogee project, which Gail has been a leader of, has been measuring the composition of stars in our Milky Way. The Baryon Acoustic Spectroscopic Survey, BOSS, and its kind of extension in the extended BOSS or EBOSS survey is really trying to find the positions of galaxies and quasars at increasingly larger distance from the Earth in order to measure structure out at greater distances than we've previously been able to probe. There was also a small exoplanet piece of the survey, which has not been quite as productive as other experiments like TESS and Kepler. But Segway was kind of the fourth of the 4 surveys, and this was really successful at mapping out parts of our galaxy that hadn't previously been discovered. So tidal streams across the halo of the galaxy is one example, and other populations of stars in our own galaxy. Now, what's currently wrapping up right now is an extension of the Apogee survey by adding observations in the southern hemisphere. We can now see the entire Milky Way galaxy from 2 telescopes, which are similar in their properties. We've extended the EBOSS survey to find more and more distant galaxies and quasars. And then also the MANGA survey, which has been really fun, has been bundling those spectroscopic fibers into tight bundles that can be placed on a single more nearby galaxy to get a different spectrum from different locations all across the galaxy. So in this way, we're able to get composition information, spectroscopic data in a spatially resolved way, and understand how galaxies are different at their centers compared to their outsides. And this has been a really exciting part of the survey as well. So that's all the data that we have. Now, what do we have for you to use in your classes? The good news is, we have resources for all ages. And I said in the title of the talk that I would focus on high school and college. But if you go to the link that's been put in the chat window, you should be able to find resources for all ages, well kind of laid out and linked all in one place. So it may be helpful for you to scan with your phone this QR code, or if the link is easier, you can use that as well. So what I want to show you are just a few short examples of things that I've enjoyed using in classes and I would highly recommend. The first of these is a data exploration using citizen science and the Galaxy Zoo platform. This is not something that our team at the SDSS has produced, but it's using our data. So I am going to include it, and also to say that I've been using it for a few years now, and it's an excellent pre-made curriculum that I would highly recommend for any undergraduate class. I'm going to just point you to where you can find some activities that are appropriate for middle school and high school age students, and then also just point you to some Python-based activities that use the Jupyter Lab environment to open up these data to students who may be able to do some more advanced computing. And finally, the Plates for Education program, those aluminum plates that we use to map the sky spectroscopically. We have a whole set of activities that are based around those plates. We're going to be talking about those this afternoon and offering anyone who comes to this afternoon's workshop the ability to adopt 2 of those plates free of charge. We will send them to you. We would love for you to have your own piece of the Sloan sky for your classes. And so we will provide those to you if you attend this afternoon and fill out our survey at the end. And we'll try to ship those off to you as soon as possible. So let me just quickly show you the citizen science project produced by Galaxy Zoo. I think maybe you've heard of Galaxy Zoo, but this was a way of getting kind of crowdsourcing the visual inspection of galaxy shapes, right? It's something that astronomers needed to do in order to understand better how the shape of the galaxy corresponds to other properties of it. But it was too much work for a couple of astronomers to look at, tens of thousands or even millions of galaxy images that are included in the Sloan footprint. So a while back, 15 years ago, or maybe a little bit more, the Galaxy Zoo project was born. This was a simple interface that allowed members of the public to look at a galaxy and say what it looked like, whether it was an elliptical galaxy or a spiral galaxy or a merger or whatever. It was enormously popular. Tens of thousands of people signed on. They classified collectively more than 1 million galaxies. And you can actually see how quickly it took off, right? So the total classifications on the y-axis here versus days since launch. So within 100 days of launching, people had looked at more than 1 million made more than 1 million classifications. And when you have multiple people making a classification of the same object, you can get a statistical measurement of how correct, what the average classification was, which is bound to be better than any one classification alone. Most people, if you look at the number of users versus the number of classifications, most people were classifying 100 or maybe even a few hundred galaxies before getting bored with it. But some people were classifying just enormous amounts of galaxies. It can be really addictive. I don't know if you've tried it or not, but it was just an enormously successful science engagement project that brought the public in to participate. And one great story to come out of this Galaxy Zoo project was Hanny van Arkel, who was a Dutch school teacher who was engaged in classifying galaxies, found something that no one really knew how to identify, and she made a comment about it in the forum, and ended up being the named discoverer of what's now known as Hanny's voorwerp, or Hanny's object in Dutch. Later, studies of this object were made using follow-up imaging, using the Hubble Space Telescope and other instruments. And we now know that this is a whole new classification of object that had not been seen before. And now that it's been identified, we're actually finding more of them. Essentially, what Hanny had discovered is an ionization echo. So a galaxy that at one time had a quasar turn on, so the central supermassive black hole started accreting matter, which made it very luminous for a short period of time. That light traveled from the quasar out to where some gas had been stripped away in the outskirts of the environment of this galaxy and ionized it, causing it to glow. Right. And so we think we understand this really well, and all the follow-up with different instruments has led to this really much better understanding of what's going on. But this had never been seen before, and it was just a member of the public who was able to make this amazing science discovery. So Galaxy Zoo has produced those kinds of interesting, weird discoveries, in addition to providing the kind of data at scale that have allowed us to understand more about how a galaxy's shape correlates to its stage in evolution, its environment, its star formation rate, et cetera. And so we've had a number of really important papers come out that have used these data and included the public in the author list. Now, that data also has been spun into a really effective curriculum that I think is great for high school and college level. So if you go to classroom.zooniverse.org, which is also included on the, I think it's included on the link that I shared, you can go and access it, and it's beautifully documented. There's a teacher's guide and a Google Drive link to 5 weeks worth of material, which are really great for student projects. So it covers topics like the HR diagram, Hubble's law, and culminates at the end of this curriculum with a group project where students actually use a spreadsheet of 20,000 measurements of galaxies in the Sloan Digital Sky Survey, which also have morphological information from Galaxy Zoo, and teaches them how to engage with the data, how to visualize and analyze it, and finally, how to communicate their findings in the form of a video. I can show you, I don't think I have time to show this whole video, but I do have one example from a group of my students in an intro level college student classroom. So this is 100 level astronomy students, and the final video that they produced after doing this curricular unit in my class.
Hello, this is Benjamin. My colleagues Samantha, Abdullah, Alex, and I will be discussing the relationship between the galaxy's morphology and its likelihood of being found in a cluster. Elliptical galaxies are usually formed by the merger of spiral galaxies, which results in the destruction of their arms and the depletion of their interstellar gas. Since a high density of galaxies would increase the likelihood of collisions between them, we wonder if there is any observational evidence that ellipticals are more likely to be found in high-density clusters, as suggested by this photo of a Bell 370 galaxy. We hypothesize that ellipticals are more likely to be found in dense clusters, whereas spirals are more likely to be found in less dense parts of space.
To test our hypothesis, we divide the Galaxy Zoo data by galaxy type, using only galaxies with an 80% consensus or higher on their shapes. From there, we performed a statistical analysis and histogram of the log of local density for each type of galaxy. Though ellipticals have a greater mean local density than spirals, the difference is small compared to the large standard deviation for both sets. The histogram for ellipticals does suggest a slight trend toward higher densities compared to the more even distribution of spirals. To further confirm or challenge our results, we performed another analysis, this time of the distance to nearest cluster for spirals and ellipticals. We found that the mean value for distance to the nearest galaxy for ellipticals is slightly less than that of spirals. However, this difference is still very small compared to the standard deviation of both sets. Interestingly, both galaxy types have 0 as the radius with the highest frequency, which suggests that a large amount of both spiral and elliptical galaxies lie in clusters. The data is slightly less skewed towards 0 for spirals, though, suggesting that a relatively higher proportion of ellipticals lie in clusters.
Both tests essentially gave us the same information. Ellipticals appear to be found more often in dense regions of space and clusters, but it's difficult to claim with statistical certainty that the mean local density is greater and the distance to clusters is lower for ellipticals than for spirals. These results, though not statistically certain, suggest that ellipticals are more likely to be found in denser regions of space or clusters. For our analysis, we assumed that the 80% consensus threshold was the best criterion for determining galaxy type, and that there was no bias in the availability of nearest cluster data, such as a greater likelihood of being able to determine a galaxy's nearest distance to a cluster if it was, in fact, relatively close to a cluster.
Our results may be expanded upon by those of a similar but more rigorous.
Okay, so I'm going to stop here because it goes a little longer than we have time for. But I just adore this project. I think the students actually end up, having an identity as scientists. They're playing with data sets that are too big for them to manage in any way that they've probably used before. And it's important to note that the only requirement of this project is Google Sheets. So with a Google account and the Google Sheet spreadsheet and a free add-on that's been produced by the Zooniverse team, all of this is possible. You don't need to know how to code. You don't need to have any specific software. It's really excellent. So I do want to show you just a couple of other things. I'm very short on time, so I'm just going to kind of speed through this. But what we've been doing in our team at SDSS is to produce some resources that are available for students at earlier ages. So a lot of what you can find on SDSS Voyages are meant for middle school level students and maybe high schoolers, although some of them at the 100 level in college could also be could be pretty useful. We have a tab here with educator guides. Our pre-flight section is really just basic background information, like what is redshift, what are filters on a telescope. These launch activities are for shorter explorations of the data that are better for younger students, and the expeditions are really designed for higher level high schoolers and maybe college level students as well. And then if you want to get away from the digital space, we do have some hands-on activities that you can find on our site as well. And we've recently been putting a lot of effort into translating this for our partners in Chile and Mexico, and we've seen a lot of traffic on the site coming from Spain. So if it's of interest to your students, we do have most of the site translated into Spanish as well. So we don't use the next generation science standards to really classify all of these activities in a way that you might be needing. And the reason for that is intentional, because our survey is international and those American educational standards don't always map to other international educators. But we do have some basic 1, 2, 3 star systems to kind of designate the difficulty of different activities. So these activities I've had great success with middle school aged students. Many of them are designed to be accessible and exciting for a younger audience. But if you have students who are really starting to be capable of doing coding in Python, we've also been developing activities in collaboration with SciServer, which is a platform of cloud-based computing that allows you to run Jupyter notebooks that are already connected to the entire Sloan database. It's free to access. It's free for you and your students to make accounts. And it's a great way of bringing computing into an under-resourced classroom. Like, we don't have access to great computing at my university, but using SciServer, students only need access to the web. They can produce an account and do all of their computing in their account online for free. So, so Rita Chigero and I have been creating some materials that are designed for undergraduates, but would be great for advanced high schoolers. One that I'll share that Rita's been working on is a lab for the 100 level students, where in only a few lines of code, they really don't need to know very much Python at all. They can just tweak some existing code to see how, how galaxies are distributed in the universe on large scales, and really get an impression for what the cosmic web looks like. With only a couple lines of code, you can actually overlay more distant, higher redshift structure with lower redshift structure to see that there is some depth to this web as well. And then again, with only a few more lines of code, you can trace out the cosmic web separately for red galaxies compared to blue galaxies. And students can really quickly get an impression using real data of how much greater the clustering is for red galaxies compared to blue galaxies, which tend to live in lower density environments. A nice thing about SciServer is it's also easy to call up thumbnails for images. So students could define a sample of galaxies based on size and redshift, and actually pull up, with only a few lines of code, the thumbnail images of those galaxies and answer questions about them. So this is a really, really powerful tool that students don't even necessarily need to have a lot of coding background to engage with. But for students who do have a greater level of proficiency in coding, I've created an upper level curriculum, which is also available on GitHub. to kind of cater to students who are maybe physics majors or at least astronomy majors or minors. And I won't go into the details of that curriculum other than to point you to where it's found and to show a few examples of students I'm really proud of who, after taking that class, went into undergraduate research projects and then later became full-time staff members at some major observatories. And so I think there really is a lot of potential for these kinds of real authentic data-based curricula to inspire students and to give them the skills to actually go on and pursue careers in the field. So I'm going to leave it there. I'm just about out of time. But I am happy to take some questions, and also please feel free to reach out either to our entire team via this outreach email address or to me personally. So thank you all.
Thank you, Britt. Keep in mind, questions may be submitted through the Q&A feature. We do have one question here already. And the question reads, the last time we were introduced to the Zooniverse classroom a couple of years ago, they showed us the Google sign-in option for student privacy, but that it was not functional and there were no plans to make it functional. Students are not able to make accounts on websites without Google sign-in. Do you know any progress on this?
So I don't, yeah, I think that might be better sent to the Zooniverse development team. I know Laura Truey at the Adler Planetarium, I think, has been leading that project. But I will say I haven't tried the project without a Google account. So I think that is probably still the case. At my university, we're really embedded with the Google Suites, and all our students have access to those accounts and the software that comes with it. So I haven't had that problem, but I would direct that to the Zooniverse team. And Molly Simon, I think, would be the person as well. So I can share her email address if that would be helpful.
Laura was here 2 years ago in the seat you're in right now.
Oh, great.
And that's what the question's referring to. Are there any other questions for our speaker? Well, Britt, I think that means that we do have a question here.
Right.
It's another Google Sheets kind of question. After we had Zooniverse at the past workshop, Google Sheets had disabled some features that were required for the HR diagrams activity. Have those worked recently?
So I discovered that on the fly while teaching with the material this past spring. They have disabled, I think, the histogram tool that had been part of the Zooniverse, the Zoo Tools add-on, which makes it really easy to do some simple plotting in their spreadsheet. The reason why they've disabled that is because Google Sheets has added a simple histogram plotting function as part of their standard set of tools. So it does cause a little bit of confusion. I've had to rewrite some of my instructions for my classes. So I sympathize. I think that is still maybe an issue, but I've made a short tutorial showing students how to make different kinds of plots. And I think that that's been helpful as well.
Another
so
comment
asking,
question regarding the SciServer account and GitHub, are the data protected and secure to be accurate scientific data sets for students using Jupyter Python coding?
Yes, so the data sets, there are a few different kinds of data sets that you can access through SciServer. One of the few is the Sloan Digital Sky Survey. So that data set is fully vetted. There are publications that describe in great detail how that data was reduced and how it's been presented. So I would say, yes, it's fully vetted. If you look at the publications page on sdss.org, you can find all of the documentation. I hope that answered the question.
So we have
as for GitHub is a very large project with open source contributions, and I cannot vouch for the rest of GitHub, but SciServer for sure.
Okay, well, our question queue is empty. I think that's because so much was crystal clear. Thank you very much, Britt. Telepathic applause coming your way.